Welcome back. So today we're going to introduce the concept of hypothesis testing in statistics. This is one of the most kind of ubiquitous ideas out there. So I'm sure you've heard of p-values and p-hacking, confidence intervals. That all has to do with hypothesis testing. And it's how we make statements about how confident we are in some statistical property of some data set. So really common examples are things like, let's say you want to test a new drug or medical treatment. So you would set up an experiment where you have a control group and a treatment group, and you would try to say something about, did the properties of that treatment group change with respect to the properties of that control group? Is there a statistical difference in these two distributions? That would be some evidence of the effectiveness or ineffectiveness of that drug or medical treatment. And similarly, you could have before and after some manipulation, you collect data. So maybe you have a factory producing some product, and before you change something in the factory, you have a certain yield of, kind of successful products generated or faulty products, and you change something in your production process, and you want to tell, did my yield change? Did my maybe average value of successful products or non-defective products, did it change after my manipulation? So these are the kinds of questions we ask and answer with hypothesis testing. Has something changed in my distribution of my data? Now, technically, it doesn't have to be before and after. I could just have a data set, and I could ask a question. Is this data set, does it belong, is it a normally distributed data set? Do these random variables come from a normal distribution? Or is the data distributed as Poisson with lambda equals 10? Those are also hypotheses that I can test and give a statistical confidence of how true or how likely that statement is to be. Okay, very, very powerful. We're going to get into a ton of examples, and this is going to give us a lot of tools for how to use the probability we learned to make really strong statistical statements about the real world and the data we observe from that real world. So let's do an example. I want to start with just a really, really simple example. We're essentially going to do kind of A/B testing where, let's say, I have some website and it gets a certain amount of traffic per day. And after some guerrilla marketing campaign, I measure the traffic for 30 days, and I want to tell, did that campaign work? Was it effective? Did it shift the mean or average amount of users or viewers per day? Okay, so we're just going to get started. So we're going to say, this is just an example. So we're going to have, a website has an average daily views or visits, average daily visits. And let's just say that this is, I'm just going to pick a number, 10,372. So 10,372 visits per day. We're going to say this equals mu. Okay, this is the average before manipulation. Okay. And after marketing, so after the marketing campaign, maybe you sign up for a pro account on social media, and you start blasting ads to take people to this website. So this is after manipulation, after marketing. We have to run an experiment. We have to collect data. Okay, so we collect a random sample of 30 days. So after marketing, we sample for 30 days and find a sample mean of these 30 days, a new average daily visits to that website. We find a sample mean of, let's say, 10,628 average daily visits. Average daily visits with a sample standard deviation, a sample SD of, I'm just making up numbers, I worked this out ahead of time, so it works, of 402 visitors, okay? So just putting some underlines on here, this is my N is 30, N is the size of my sample. My sample mean, X bar, is 10,628, and my sample standard deviation is 402. So this is the basic problem. Just we had an old mean or average value, and we changed something. We did some marketing. After manipulation, we have a new observed mean over some sample. So we sample 30 days. We assume they're independent. That's a little bit of an assumption, but we assume that each day is independent and random. For 30 days, and we get this new sample mean and standard deviation. So the question is, did something actually change, or was this change just due to statistical fluctuations and random chance? Is this expected based on this mean, or is this really because of a successful marketing campaign? That's the kind of question we ask. And so the way we write this down statistically in terms of hypothesis testing is we state two different hypotheses. There is what's called the null hypothesis, that nothing changed. So either A, the mean hasn't changed, the mean has not really changed, and the observed difference is due to statistical fluctuations, and this increase is due to statistical fluctuations, just randomness fluctuations, kind of expected statistical fluctuations. We know that things are distributed and have a spread. This is called the null hypothesis. The null hypothesis, you've heard about this before probably. And we typically give this a symbol or a name. Often it's capital H sub 0, the null or 0, kind of the baseline hypothesis that nothing has changed. And the other hypothesis, the kind of counter to this, the complement of this from a probability standpoint, is that actually the mean has increased. The mean has increased, meaning that this observed sample average is unlikely to be due to statistical fluctuations. So it's kind of, too large of a change for statistical fluctuations, for it to be kind of random. And this is called the alternative hypothesis, the alternative hypothesis. And sometimes we give this a name, we call it H underscore A. And I realize in A-B testing, really that should be called B-A testing because it's before and after would be the A. The A's and the B's don't work, just, anyway, there are two hypotheses, a null hypothesis and an alternative hypothesis. And these are complementary sets from a probability standpoint. Either A is true or B is true. There's no other possibilities. Either nothing has changed or something has changed. Those are the two possibilities. And so what we're going to do is calculate using essentially what we learned in probability and kind of models of X bar and things like that. We're going to compute kind of a likelihood or a confidence interval or some significance of how likely it is that the mean has not changed, and that will either support or kind of refute these hypotheses. Okay, and remember, just like in probability, it's often very hard to compute the probability of something happening, like the probability that there's a change. There's a million ways this distribution could have changed. It could have changed the mean in lots and lots of ways to get this observed value. This is almost impossible to compute. This is actually really, really easy to compute. And so kind of roughly speaking from our probability, this alternative hypothesis has probability 1 minus the probability of my null hypothesis being true. So I'm going to compute this guy and use that to say something about whether or not this distribution has changed. Okay, good. And the answer to this question of has something changed, we're going to use the central limit theorem. So this x bar quantity, this x bar, is going to be a normally distributed random variable. We know that as long as n is large enough and 30 is large enough, then x bar is going to be normally distributed around its value of 10, 6, 2, 8. And it's going to have some spread, some standard deviation or variance related to this sample standard deviation. And what we're trying to figure out is, is the actual mean close in this distribution to the sample mean, or is it really, really far away? Is it many standard deviations away? That would tell us if it's likely or unlikely that this was random chance or if something changed. You're probably tempted to compare the difference between these two, which is, I don't know, it's about 256. You're probably tempted to compare the difference between the sample mean and the previous mean, 256, with this sample standard deviation, 402. And you might conclude incorrectly that this difference is small compared to this standard deviation, so not that much has changed. But what you actually need to compare against is the standard deviation of the sample divided by square root of n. Okay, so that's actually what you need to compare this delta to 402 divided by square root of 30. That tells me how many essentially standard deviations away x bar is from mu. And that's what we're going to do right now. We're going to go through the procedure of hypothesis testing and actually compute a number for how confident we are, what percentage confidence we have that something either changed or didn't change. Good. So the procedure. Now we're actually going to get into the procedure of hypothesis testing. Okay, so we have a hypothesis that we want to test. It's whether or not my daily average visits of a website has actually changed because of my guerrilla marketing campaign. I have some numbers. I'm going to actually be able to compute this. And so there's some steps. We first establish our null hypothesis, which we've done. And we assume, that the null hypothesis H naught is true. H naught is true. We assume the null hypothesis, basically that the null hypothesis is that the average is still mu equals 10,372. And that this is, kind of within the realm of possibility given this mean, that's the null hypothesis. Okay. 2, we determine what's called a test statistic. Okay, so 2, we define a test statistic that essentially is going to give us an actual probability test. And again, remember, this x bar is distributed as a normally distributed random variable by the central limit theorem. And so we're going to use a normal distribution to test the statistic, okay? So we define a test statistic. And I'm just going to tell you what that is right now. The test statistic is essentially this value z, which is the observed mean. This is the observed x bar, minus the hypothesized mean, the expected average. So the observed average minus the expected average divided by what's called the standard error. And the standard error is going to be this standard deviation divided by square root of n. And remember, if you need to go back to the lecture where we characterized this x bar, we computed the mean and the variance of x bar. And the standard deviation of x bar, called the standard error, is just the sample standard deviation divided by square root of n. So as I increase n, that should tighten, right? That should get smaller and smaller. So I need to divide by square root of n in this quantity. So this is literally equal to x bar minus mu divided by this sample standard deviation. I'm going to call it, sigma hat divided by root n. This is going to be what's called my sample statistic. And remember, because x bar is a normally distributed random variable, we can subtract this mean, divide by the standard error, and now z should be a unit normal distributed random variable. It should be Gaussian with mean 0, standard deviation 1, which means we can use our lookup tables and our cumulative distribution functions to calculate things about the likelihood of z being less than some value or greater than some value. Okay, and so maybe I'll actually just put in some numbers here. So this z is going to be equal to this number, 10,628 minus 10,372 divided by 402 over root 30. And this is approximately equal to 3.49. And we say 3.9 standard errors because that gives us some context. What that means is that if the mean was whatever, let's write this a little differently. If the mean value was 10,372, then my observed value of x bar being 10,628 would be 3.49 standard errors or kind of standard deviations away from that mean. And 3.49 standard deviations is a lot. That's pretty unlikely. We're going to use our lookup table and compute how unlikely this is, but it's very unlikely. Anything more than like 2 standard errors is very, very unlikely. 3 is kind of, super duper unlikely. And so that's what we're doing here. We assume the null hypothesis. We define a test statistic. We say, if the null hypothesis is true, what's the likelihood that x actually follows this distribution, with mean mu, given this standard error? And I get some number of standard errors of x bar away from mu. That tells me how likely, how kind of far away those two are. Good. And if you like, you could also say, I have a distribution around x bar. How likely is it that mu is in that distribution? Those are kind of equivalent statements. Okay, and then what we do, the third thing, is we actually just compute how likely this is. We compute what's called, this is 3, we compute the observed significance level. Compute the observed significance level, and we call this p. This is not, capital P, the probability, it's little p, it's called the p-value. You've heard of p-values before, like 0.95, 95% confidence, 99% confidence. That's the significance level, or p-value. And so again, by the central limit theorem, we assume that we have this Gaussian distribution. I'm just going to draw it again over here. So we assume that we have this Gaussian distribution, and because we've subtracted off the mean divided by the standard error, z should be a unit normal Gaussian, and our observed value is way over here at 3.49 standard errors away from the mean of 0 in this normalized z coordinate. And so what we're trying to compute is what is the error what is the probability that we're 3.49 or more standard deviations to the right of this mean? What's this probability here, okay? And so you can compute what's the probability that z is less than or equal to 3.49. That's all of this stuff to the left of that. And this is something you can look up in your handy, stats book, or you can, I don't know, go to Wolfram Alpha, or, in Python, in scipy.stats, you can do this, or Ask GPT. This is an easy thing to look up. This is tabulature. This is known. And so I go to table 2 of my statistics book, and I look for the probability, the cumulative density function of a standard unit normal, that z is less than or equal to 3.49. 3.49 is 0.9998, okay? 0.9998. So this equals 0.9998, which means that there is a less than 0.02% chance that my sample mean would be this large or larger given this previous mean and this sample standard deviation. So this is my p-value. Actually, my p-value is the small value. So the p-value is this little tiny number, 0.0002. This is my p-value. And the probability, it's the probability of this null hypothesis being true. The probability of my null hypothesis being true is 0.0002. That's my p-value. That means it's extremely unlikely that the null hypothesis is true. So we say that we reject the null hypothesis. That is the way that you say it if you want to sound legit, is that if your p-value is small enough, meaning that the probability that this data came from this distribution, if that p-value is small enough, then you say that you reject the null hypothesis. And that means if the null hypothesis is not true, then the alternative hypothesis is probably true. Okay. Now, we have not proven that this comes from a different distribution. We have just said that it is very statistically unlikely that the distribution hasn't changed. It's very likely that the distribution of average daily visitors has changed. We haven't proven that it has, but we've said that assuming the central limit theorem and the data collection was correct, based on our assumptions, there's less than a 0.02% chance that this data came from the same old distribution where nothing changed. So that's that's the power of hypothesis testing, is that you can put a number to how likely some hypothesis is. There is a 0.02% chance that the null hypothesis is true, and a 99.98% chance that the alternative hypothesis is true. Okay, good. Now, there are a lot of other things. We still haven't said what the new mean is. We don't know what the new expected average daily visits are. This is probably my best unbiased guess right now. And it has its own statistical properties. But this hypothesis testing didn't tell us, for sure what the new mean was. We could develop a confidence interval for if I wanted to be 95% sure that my new average daily values is between a certain level and another level, I could build a confidence interval based on the statistics of X bar. But that's not what hypothesis testing does. It just allows me to write down a hypothesis that nothing changed and either support or reject that null hypothesis. Last thing about p-values. So we want small p-values are evidence to reject the null hypothesis. Are evidence to reject the null hypothesis. Are evidence to reject the null hypothesis, H naught. And so typically if p is less than 0.05, we say that this is a statistically significant, significant. You'll hear this a lot now, significant. We say specifically that HA, the alternative hypothesis, is statistically significant. And if p is less than 0.01, we say that it's strongly statistically significant, HA. So if I run a medical trial, if I have some new wonder drug for cancer treatment or for weight loss, and I run a big test with a big N, and I get a p-value that's less than 0.01, that would say that there is strong statistical significance in the hypothesis that that drug is actually effective. Okay, and that's how you use this p-value. Now there is a lot of danger. People in research groups, medical groups all over the world, because the p-value allows you oftentimes to publish your results or not publish your results, to have people believe you or not believe you, to have people spend hundreds of millions of dollars on your drug or not. There's a lot of motivation to manipulate your statistics to get a p-value that's significant or strongly statistically significant. This is called p-hacking. It's a really, really pernicious form of lying with statistics. We're going to talk about it in a little bit, but at least in this simple example, you can see the basic idea of how to form a null hypothesis, how to take a hypothesis, how to form a null hypothesis, and then test that null hypothesis and actually get a number out of how confident you are that you either should accept or reject that null hypothesis. Okay, thank you.